you're going to meet my favorite arthropods. Seriously, they are the coolest. Their fancy name are the pycnogonids, but you may have seen them as sea spiders. And they are definitely not spiders, but they are absolutely fascinating, and they're some of the coolest looking little things on there. And rather than get copyright claimed, let's just pull up a picture of a pycnogonid. And there they are. And so think more like a crab than a spider. They're absolutely gorgeous. And there's a couple really cool things about them. So this one you can tell is a male because males actually grow an extra set of arms. So these little arms right down here, we're going to see. And the arms wrap around a little ball of eggs. So it's the male that actually has to carry the little ball of eggs around. So here's another male holding onto a ball of eggs with that special extra set of arms. Wouldn't that be cool if when you were having babies you could just grow an extra set of arms? That'd be very useful. And their eyes are wonderful, and just their insides are wonderful. We're gonna go see these. So they are actually nothing like spiders. They just have a little bit of that similar appearance, but it's like they're missing the entire sort of head and body of a spider. It's like they decided to go with all legs as the acceptable solution. All right, so let's talk pycnogonids. And so here, let me walk you through your videos. So these first 3 videos are going to show you some sea spiders. And you're going to see them, and you're going to see how beautiful they are. The next one, you're going to see a sea spider swimming along, because they can swim, and they just move their little spidery legs while they do that. The next one is a video from the Mbari. It's the Monterey Bay Research Aquarium. And these guys are looking at the deep sea. And so it turns out that pycnogonids will actually fall, and they will adopt this special sort of star conformation where they'll hold their legs up over their heads, and this helps them to fall down great distances relatively quickly. And so if they're on the up in the shallow water and they want to get deep really fast, that is how they do it, which is very cool. So they call it the comet posture, when they fall. Then you got a lovely male with eggs here, and some well camouflaged pycnogonids here. There's some of them that are just covered with little bits of algae, and they look exactly like the stuff they're on. These are really tiny. If you've ever been to a tide pool, chances are there were some pycnogonids there, but you probably didn't see them because they're little and they like to hide. These are not fearsome predators. They're little prey species. So let's go look at our PowerPoint, and let's start it up so we get all the words appearing. There we go. This is a family tree of modern arthropods and pan-arthropods. So pan-arthropoda is everything that's in this tree. And so that would include our onychophorans, which are also called velvet worms. And it would include our tardigrades, which are also called water bears. And then inside Arthropoda, so everything downstream from this branch is a proper arthropod. Over here on this side, we have the really primitive ones. And so the absolute most primitive branch goes to Pycnogonida. And that's part of why I like them. They preserve a lot of really weird primitive features that you would tend to see in fossil organisms, and they're just missing from all the more common things. Also down there, we're going to have things like Xiphosaura, which are going to be your horseshoe crabs. You're going to have your scorpions. You're going to have your ticks and mites. You're going to have your whip scorpions and vinegar scorpions. You're going to have your actual spiders. And then over here, the next branch is going to lead you to your, everything down here is mandibulata, so all of these guys. But the myriapods are going to be things like millipedes and centipedes, and some other friends that you probably wouldn't see every day. The next branch down is the pancrustacea. So these are all the things that are basically crustaceans. And weirdly, insects are part of that group. So insects are a modified crustacean, which is kind of cool. But you're going to have all these other little tiny groups over here. Things like ostracods, those little water fleas, or this is one kind of thing that you could call a water flea. There are other things which are different from them. And the next branch, you've got little things like copepod. And so I would imagine you may have found a copepod and or an ostracod in your just water sample from the pond. But also in this group, you would have things like decapods, which would be crabs and lobsters. And then the next branch that is on our way to becoming insects. Insects are kind of the most recently evolved of the bunch. You're going to have these things that are called Remipedia. And Remipedia look a lot like a centipede. But the way they're put together and the way they develop, and their DNA in particular, tells you they're related to insects. So these are aquatic. They are only found, most of them are actually only known from underwater caves. So like a cave that is totally submerged, they tend to be in there. Some of these tend to live near the freshwater, saltwater interface in those caves, because often there'll be sort of a path into the cave where groundwater that's freshwater will seep in and it'll kind of sit on top of the salt water. And these guys seem to love that. So as rare and weird as they are, they seem to be as close as we can get to the bottom of the branch that leads us to the insects, which is really neat. And then once you're into this group, these are going to be insects pretty much from here on down. There are going to be various things like springtails, for example, or like earwigs, or like silverfish. And these are primitive branches. And then you get to the normal like hexapod insects, six-legged, normal type insect things that we all know and love. And there's only a couple branches on here, but yeah, really, there's a lot of branches on here. These guys are super numerous and extremely successful. Probably as much so or more so than everything else on the chart put together. But first, let us talk about the beautiful, beautiful pycnogonids. So look up here at the front. We've got, so these chela are going to be like chelicera. They're going to be similar to those sort of feeding, pinching appendages that we get in something like a spider. And also they're going to have palps here. And so this proboscis is going to be segment 1, presumably, as it's developing. And then segment 2 are going to be these chela, and segment 3 are going to be the palps. And then for some reason, segment 4 back here is where you actually get the eyes. The eyes come up in a very interesting position. And the eyes are on this little thing. It's like a little pod, kind of like a conning tower on a submarine, maybe. And it's got a cluster of eyes that point in different directions and do different jobs. Then we're going to have our 8 legs, which is really 6 in the middle and 2 at the back. They have a little tiny abdomen, which is just like a little point, kind of like a dog's tail that sticks up, which is, of course, adorable. And then if it's a male only, the females do not have this extra set of legs, but if it's a male, it will have the extra set of legs. And they are called an oviger, and they are for handling eggs. They're the special egg-clasping appendages. Okay, so here's one of the pictures that we would have seen online. So here are the ovigers, and there they're holding on to a little ball of eggs. Up here at the front, you can see the different parts of the head anatomy, which are actually quite different from a lot of the other arthropods. We think these are a weird side branch that has somehow persisted to the modern day, despite being really rather primitive. Yeah. As far as I know, I haven't seen an actual genome sequence from one of these pycnogonids yet. I would expect it to place them pretty far down near the bottom of the tree. I think that tree that we were looking at was just made based on a couple of genes, but we'd have to go look in the literature. Yeah, things change all the time, and you can never say for sure that something hasn't happened. Just, you know, that it hasn't happened that you have seen yet. Yeah, and so here are the different body segments, and yeah, that little pod, number 4 there, with the eyes on it is just really neat. Here you can see the embryo, and so the embryo has those big sort of pincers up front. Here are the other claspers that go around that. This is the thing that's going to be that little sort of pod with the eyes on it later. And here are our first modified legs that are actually going to help this thing to move around, and those are going to then become, I believe, the ovagers. But it's going to go through a pretty substantial metamorphosis to get to the end. And look at its little tiny abdomen. It just kind of stays the same size. So here it is as a baby, and it's pretty much full size. You can actually see the individual bacteria. Look at those little rod-shaped bacteria that are tucked in the crack of our little baby butt right up here. So pretty nice. Here are the eyes, and the eyes are amazing. So here's that little pod right up there. And so we're going to have an eye at the front, and these big eyes at the front actually are very good eyes. And then on the back, we'll have a kind of a not great version of an eye, but it's going to be an eye that can kind of tell you if there's something coming from behind you. It's sort of a, you know, watch your own back kind of eye. And there's going to be a pair of these on either side. If you look at the inside, we've got a nice little, nice little eye. And so it's going to have all that pigment going on at the back, just like normal. These little slices are through the top, middle, and bottom of it, as you can see here. They're counting up all the nerves that are coming from the back of the eye. So yeah, it's well innervated, like lots of nerves back there. And so there's probably a lot of signal that's flowing into the little tiny pycnogonid brain. And here is that pycnogonid brain. So the brain's going to be located right here, and so this is actually marking what is probably the embryological front, like the actual front during development of the body. The brain are these two sort of orangey things right back up here. And there we have little ganglia on the side that are going to go off to run the mouth parts. And then as we go toward the back, it's going to be the same sort of deal as any other arthropod. We'll have that sort of loop that goes around, and we'll have great big ganglia, these nice little yellow things, every place that a leg is going to go off. And so we're going to send off a new branch of the nerve. And yeah, we're just going to store all those nerve cell bodies in a blob that is a ganglion. And that's how arthropods in general are going to work. Here's a picture of the inside of just the nervous system of an embryonic, or at least larval, pycnogonid. And so you can see that there are nerves that run all the way up into those little front claws. Let's see, they didn't call them chelicerae. I forget what they called them. Cheli or something like that. Or chelifera, I don't know. Anyway, the actual brain is right down here with the two arrows pointing to it, and so that's the control center for all of these. And so really the brain is kind of like one big ganglion, a big bilaterally symmetric ganglion. But you can see here back toward the back of the body, you have all of these nice little ganglia, posterior ganglia. And each one of these is going to be connected up to a bundle of nerves that are going to run to one of the legs or one of the parts that's going to be growing. And so as these things are going through metamorphosis, they don't just change on the outside. They have to reroute some nerves and build new ganglia, and this takes a bit of time. That's why metamorphosis is, it takes a little time for arthropods. Okay, here's a sort of close-up of the brain, and this is comparing the brain and visual systems in onychophorans, so these are the velvet worms, and xiphoceurids. These are things like the horseshoe crab and pycnogonids. So these are three, this is a pan-arthropod, but not a true arthropod. And these guys are both very primitive arthropods, but we think pycnogonids are maybe just a little bit more primitive. And so this is showing where the brain is and where the eyes connect. So the eyes are here, and then they hook up to the rest of the brain. That's right there. And there you get your little sort of ring-shaped or blob-shaped brain. On the second one, the xiphoceurid, the eyes are still hooked up to the same part of the brain, but there's a long stalk that comes up. And so the eyes will actually be on the outside of the shell, pretty far away and back from the brain. But it's still the same exact thing. And so, yeah. Let's see. And then on the pycnogonid, even though it looks like their eyes are coming out of the fourth segment, The eyes are actually coming out of the brain. The brain's located right up front, as it is in all arthropods. And there's just a big, long sort of trail that goes back, and that's what's going to lead to these little visual nerves, essentially. And so it's the same brain, the same structure. It's just you put a longer string on the eyes, and you can move them to some other part of the body. That is the idea. All right. So there are other arthropods that are down there in the primitive side. This is one of them. It's a thing called a Pentasdoumitt, and there is a disease. It's a fairly rare disease, but it's called ocular pentasdoumiasis. And this is when people get one of these Pentasdoumitt arthropods. It'll enter into their body, and it will move up into their eyes, and it will actually swim around and mature in their eyes, and have its little babies in there. And it can lead to blindness, as you might imagine. These are just some cases, and this is the result. You see a few of them here ended up with their eyesight intact, but in most cases they ended up with their eyesight severely damaged. And so you can have this thing, it's kind of like a little bug that it resembles one of the face huggers from the Aliens franchise, if you're familiar with something like that. It's got basically 4 appendages, or maybe 6 up front. And actually, no, 4 appendages up front, and then a big long tail that's like the 5th appendage. This is the little larval form. That's the form that you get in people's eyes. And yeah, it's terrible. I'm not going to show you or link to a video, but if you want to see a video, it is something else. Go to YouTube and look for Pentasdoumiasis. Just like that. And yeah, you'll see it, and you'll see them taking these out of people, or you see it moving around in people. Okay, next group. So, this is a horseshoe crab. Horseshoe crabs are in the Xiphosira. That starts with an X, and yeah, it's nothing like nothing like the automatic captioning is trying to spell it. Xiphosira, why the heck not? Anyway, yeah, so the brain is actually located up front, and then the eyes go on a long string that goes all the way back here, and boop, pops out just right there. And so that's fine. They're all part of this same head. Underneath, oh, pardon me, the mouth is here, so this is where the food is supposed to go. The first leg is up here. This is going to be a modified mouth part, but in front of that, you've got the chelicera. And the chelicera are going to be there. They're like little pincers, like little crab claws, to put food into the mouth. That is the reason why they are there. And they also have ventral photoreceptors, so something equivalent to an eye on the underside. So in case they do get flipped over, I guess, or to see what it is they're about to put inside their mouth. In addition to their nice big compound eyes, they will also have individual, so simple lateral photoreceptors, so something like an eye spot up here, and they will have a simple eye located roughly front and center. It's not particularly easy to see. We do have a bucket of these, and so normally I would be getting one of these out, and we'd be looking over it and, you know, sort of flipping it over, checking out the parts on the inside. They have this neat thing called a book lung here at the back, where you'll have the lung broken up into several, or the gills rather, broken up into several different sections, each with its own little armor plate over the top. And you'll get differences in the shape right back here, depending on whether it is a male or a female. And so, yeah, they're going to have 5 legs on each side, and a big long, their tail segment is modified into a long spike, and they use it to actually flip themselves back over, because they can bend a little bit between the head and the thorax section, and they can bend quite a lot between the thorax and the tail section. And so they will just rotate that around, and yeah, they're very adept at flipping themselves over. They're not using this as a weapon particularly. So here are some of these little beauties, and there you can see on the inside. Yeah, have a look at that lung. This is going to be similar to the kind of lung that you would find in spiders, except that they keep it more on the inside, if I remember correctly. Your little tiny chelicera are going to be up here at the front, these little itty-bitty guys. And then you're going to have 5 sets of legs. 1, 2, 3, 4, 5. Oh, so sorry, that was the first leg I was looking at. These teeny weenies right there and there. There we go. Those are the actual chelicera. And it looks like these two may be getting ready to mate. That might be what they're doing there. So why do we care about these? Well, you know, for one thing, they're awesome looking. Yeah, that's enough reason to care, isn't it? For another reason, horseshoe crabs are very useful in the pharmacology trade. So horseshoe crabs have a different sort of immune system to the one that we have. So instead of the regular coagulation system that we have that uses all these different factors, so factor 7 and 9 go to make factor 10, which activate it rather, which then activates thrombin, activates fibrinogen, which cuts fibrin or something like that, which leads to blood coagulation. And so that's the idea of our coagulation. And in horseshoe crabs, they have these things, these coagulagens, which are going to be right down here. And what you can do is you can take a little bit of horseshoe crab blood out, and it will actually coagulate in response to the tiniest amount of bacteria. So if you're at a pharmacy preparation facility, they can't check the sterility of the entire bag of solution. Say they're preparing an intravenous drip or something like that. But they can take a little bit of it out, or if they're making a big batch, they can take a little bit of the big batch and just check that there isn't even a trace of the bacteria in there, because lipopolysaccharide, LPS, is one of the components you're going to find on the surface of many bacteria. And that is an extremely good activating factor. And so what's going to happen is you're going to set off their coagulation cascade, and it's going to lead to the coagulagens being activated and forming a little clump, basically coagulating. So you take a little bottle of this beautiful blue blood, that's the color of the blood in the horseshoe crab, and you add in a little of whatever pharmacological solution you've just made, and as long as everything stays in solution, then you know that everything's fine and you have no bacterial contamination. So very useful, very expensive product, and there's a place in Virginia I know that grows these things and milks them. It just takes a little bit of blood out of the adults, a little drip, and then puts them back in the ocean, and they're fine. And it'll harvest them again next year. And yeah, they sell a lot of this stuff to labs around the country and around the world. Very useful. So here's the idea. Your coagulagen is going to lock together, and you'll have the head of one binding onto the tail of another one. There's a thing called the peptide C, and this peptide C gets chopped out in the activation process. Once it's chopped out, you're just going to have these things linking up into big, long fibers, and so that's how they make the fiber. In a mammal, we have fibrinogen and thrombin, which are going to polymerize and make these little fibers, and so we're going to join these fibers together. So we make sort of a net, and they make something like strings, but you know what? It works either way. It stops the blood from flowing out. And yeah, just two different ways of doing the same thing. So in case you wanted to know about their coagulation cascade. And that's the end of this section. Thank you very much.